Hello everyone, and welcome to today's webinar, Smart Chart webinar series focused on TOF-SIMS. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Ian Mowat, Vice President, Materials Characterization at EAG Laboratories.
Hi there. Good morning, everyone, and good afternoon, depending on where you are. Thank you for tuning in to today's presentation in our latest webinar in the Smart Chart series. Today, we'll be talking about time-of-flight secondary ion mass spectrometry. That's TOF-SIMS, to keep it shorter. And we'll take a walk through that technique and look at its relationship to the other techniques on the bubble chart. Okay. I'll just say a little bit about myself. My name's Ian Mowat. I'm a Vice President here in the Materials Characterization Service line at EAG Laboratories. I've got over 25 years experience in TOF-SIMS and other surface mass spectrometric techniques. I have a PhD in chemistry from the University of Edinburgh in Scotland, and I joined EAG in 1996 when it was still Charles Evans and Associates. And during that time, I've worked in the TOF-SIMS group, the SIMS group, the FTIR group. I spent some time in sales and marketing, and since December 2015, I've been leader of the Materials Characterization group, which incorporates about 16 different techniques and 4 locations. So to run down the topics for today, we'll give a quick introduction to EAG. We'll talk about our Smart Chart and then look at the fundamentals of TOF-SIMS and its relationship to dynamic SIMS, one of our other main techniques here. We'll look at the principles of operations, and we'll look at some real-world examples showing the types of data you can get from TOF-SIMS, which include mass spectra, ion images, and depth profiling. And through that, we will hopefully illustrate to you its utility as a problem-solving tool in technology-related industries. We'll talk a bit about its strengths and limitations, and also I'd like to touch on some of the complementary techniques to TOF-SIMS as well. Okay, so a quick bit about EAG Laboratories itself. We're a Eurofins company, and we have locations around the world. The orange dots here in the US, Europe, and Asia are our various different lab locations, and the blue dots are some of the sales locations we have in the UK, Australia, and Asia. So TOF-SIMS is actually located in 3 places within our network: in Northern California, in Minnesota, and in our lab in Eindhoven in the Netherlands. So one of the advantages that we have with all these locations around the world is that people can get local access to laboratories or salespeople in hopefully the same time zone as them, so they can have real-time conversations. And if we don't have the technique in your specific location, we will get the samples to the right lab for you. Another advantage we have of having these things in different locations is that if anything happens in one location or another, we can move samples between sites and things to still meet your turnaround time requirements. So there's a long list here of our various locations, but like I said, TOF-SIMS is in California, Minnesota, and Eindhoven. Okay, so here's our Smart Chart, formerly known for a long time as the bubble chart after these bubbles on here. But SMART is spectroscopy and microscopy analytical resolution tool. I think it's also useful, if you remember, is show me all the right techniques. So there is a lot of information on here that we feel is a useful way to present some of the things we do to our customers and people who send us samples. So it's important to understand the various axes on here. So the horizontal axis, the x-axis, is a measure of the dimensions of the analytical tool of interest, ranging from a centimeter down to 1 angstrom. The y-axis, the vertical scale, is the sensitivity range of the technique of interest, ranging from 100 atomic percent down to part per trillion, 10 part per trillion, or from 5E22 atoms per cubic centimeter down to 1E12 atoms per cubic centimeter. So that's basically demonstrating where any one of these techniques is active in terms of its analytical size and the detection range it operates over. A couple of other pieces of information that matter here. The blue color generally corresponds to techniques which give elemental information only or atomic information, and the red or orange color corresponds to techniques that give you some molecular or organic information. A brief word about the things outside the main box. Over on the right-hand side here, these are techniques which generally only give you a concentration measurement, and they don't necessarily have a spatial or dimensional aspect to them, only concentrations. So they're outside the box on this side. And the techniques down the bottom here are generally imaging techniques or imaging-related techniques, which are only giving you a dimensions or distance measurements and not necessarily giving you concentrations. So it's a complicated graph, but we can send you a poster of these, for example, if you're interested, and lots of people have these up on their walls. For TOF-SIMS specifically, it takes up a large central portion of the chart, which makes it look very important, which since I worked in it, I would say it probably was. So it has a measurement range from just about the millimeter scale down to submicron, and a sensitivity range from 100% down to certainly sub-part per million and into the part per billion range. If I wanted to summarize TOF-SIMS in a succinct way as possible, I'd say it's a very surface-sensitive technique providing full elemental and molecular analysis with excellent detection limits. So due to its central position in the chart, you can see it overlaps very strongly with a bunch of other techniques that have either been covered in earlier webinars or will be coming up shortly. So it's a very central technique in more ways than one. Okay, let's move on here. There is another dimension we need to remember. So previously we were just talking about the sort of X, Y dimensions on the samples, but the Z direction vertically into a sample is also very important when choosing the right analysis technique. I would say TOF-SIMS, from a elemental analysis point of view, is one of our most surface sensitive techniques, with the information only coming from the top 1 or 2 monolayers of species on the sample surface. So really on the angstrom scale. Its closest relatives are Auger and XPS, which are also very surface sensitive, but even they go a little deeper than TOF-SIMS just when you're analyzing directly on the surface. Some of our other techniques go much deeper. So again, when you're choosing the right technique, it's very important to bear in mind that there are more than just 2 dimensions. Okay, let's talk a little bit about some of the key applications of TOF-SIMS. So it's a little bit unique in that it can provide organic and elemental information basically simultaneously. So that's how I would contrast that strongly with some of our X-ray techniques or electron beam techniques, which generally are elemental only. It can also provide mapping or imaging of the distribution of those surface species, because we can focus the ion beam on the surface and know exactly where the secondary ions came from, and from that we can identify the different location of the species and hence get nice maps. It has very low detection limits, sub-part per million in many cases, so that can give you trace or contaminant levels quite nicely, and you can measure, but you can certainly identify them, if not know the exact concentration. We'll talk a little bit about quantitation later on. When it comes to failure analysis, TOF-SIMS is ideally placed for looking at problems that involve touching surfaces or the properties of a surface. So adhesion of materials, contaminant levels on materials, and coatings of materials where you are trying to adhere things together. These are great areas for TOF-SIMS to provide useful information. Due to its sensitivity, it's very good at evaluating cleaning processes from a QA or QC point of view, and it's very helpful to identify stains, discolorations, hazes, small particles, unusual features on surfaces. Okay. This slide talks about the different analytical modes of SIMS, secondary ion mass spectrometry. EAG is well known for doing dynamic SIMS. That was what the company started doing. And we have a large number of dynamic SIMS mass spectrometers, which are usually magnetic sector or quadrupole instruments. In this case, the primary ion beam operates with a DC current with a reactive primary ion, often cesium or oxygen. This means that you have material removal during the analysis. It's quite energetic, so it leads to elemental analysis only. And because we're going deep into the sample, you get a depth profile. The nature of the mass spectrometers mean you need to choose the specific species of interest you're going to monitor. It is not a survey technique. I'd like to contrast that with TOF-SIMS. Dynamic SIMS is named that due to the real-time erosion of the sample. Static SIMS, another name for TOF-SIMS, is done with a pulsed ion beam, and the static part of the name comes from the fact that you are completing the analysis before you destroy a significant proportion of the surface. So in general, you want to be damaging less than 1% of the surface to be operating in the static SIMS mode. So in general, when you're using a pulsed ion beam, in this case, gallium, gold, or bismuth are the common ions used for that. There's no material removed. So you really are only creating secondary ions from the material in the top 1 or 2 layers on the surface. Because it's not such a high energy process and there's no current, no high current involved into sputter the species, you actually get a mixture of elemental, molecular, and some inorganic information from the surface. So you would not only get information about the material you were looking at, but you'd get some information on the potential species adsorbed on top of that material as well. By nature of the mass spectrometer, it's a survey technique. So on our next page, we're going to talk a little bit about the time-of-flight mass spectrometer itself. Okay, so the way this works, and we have a couple of different instruments, but the sample is held in a high electric field. The primary ion comes in and secondary ions are created. Primary ion and then secondary ions are created off of the surface, and they fly down this region here, which has no electric field in it. This is called the field-free region. Light ions, let me just play that animation again, hopefully you can see that. Light ions travel significantly faster than heavier ions, and that's because they all receive the same amount of kinetic energy because their masses are different, their velocity is different. And from measuring the time of flight to travel to the detector, we can create a mass scale. It's this is a simplified version of the equations used, but it's basically done automatically in the background once you've calibrated your spectrum. So each pulse of primary ions on here produces a lot of secondary ions, which all fly down to the detector and hit it at different times. There's no filtering of choosing ions which you want to measure or anything like that. You get what you see, or you see what you get, I should say. Okay, let's move on to look at some of the practical instruments that we actually have. Okay, so this is an instrument from physical electronics. It looks a little bit more complicated than the last diagram, but the principle is the same. Primary ion here, secondary ions fly out, and in this case, we're making them go round in a circle to the detector, and this circular path is designed to compensate for any spread in kinetic energy from the desorption or sputtering process when the ions come off the surface. Basically, things going a little bit faster take a wider circumference path, things going a little bit slower take a tighter circumference path, and they all come together at a detector to give us nice sharp peaks. This instrument design was actually done by Charles Evans and Associates in the 1980s when we actually sold instruments in the distant past. Okay, the other instrument we have is from a company called IONTOF. Much the same principles again, primary ion here, secondary ions are extracted out this way. And instead of them coming to a detector here in a straight line, we actually bounce them out of this ion mirror or reflectron, and they come to the detector. So ions travel like this. And the purpose of the reflectron or ion mirror is exactly the same as the circular path on the other instrument. It's to compensate for any spread in kinetic energy that the ions have when they leave the surface, to let us get nice sharp peaks in the mass spectrum so we can identify the species present. In practice, these machines look a lot different. There are lots of things like cables, feed-throughs, pumps, power supplies, etc., that make the instruments look a lot more complicated. So various cables and wiring in here, windows and things. But in general, the sample's inserted in here, pumped down with a turbo pump, inserted into the mass spectrometer. There's a primary ion gun, and the ions fly up and down to the detector. Similarly, this is a similar instrument from IONTOF, but with a large state sample holder where we can take up to 300 millimeter wafers. This is the TRIFT instrument from physical electronics. Samples into the intro here, they sit vertically and fly around here, round in a circle to the detector, which is mounted back here. So we have a range of instruments from both manufacturers. They're both great instruments, and we like them both. Okay, moving on. So here's what the data actually looks like. These primary ion comes in, it's rastered across the sample. In most cases, we use a random raster scatter. So it covers the full array, but not sequentially. So it doesn't scan like an old cathode ray tube in lines. It bounces around. But because we know where each ion is incident, we can reconstruct an ion image from the secondary ions which come off. This is a total ion image, which is the sum of all of the ions. These are not mass separated. This is just all of the ions created. Similarly, we get a total area mass spectrum from all of the species present within the analyzed area. So next step, we can do a couple of other things to get some more chemical specific maps or location specific spectra. So if I look at my total mass spectrum and I think, you know, this peak's kind of interesting and this peak's kind of interesting, I can put my cursors around those and I can get a map of this species XY distribution and this species XY distribution. And you can see that they are different. In this case, we've got a ceramic blend, and the different species in the spectrum have different physical locations on the sample. So where this species is bright, the other species is dark, okay? The other thing we can do in imaging mode is to look at the total ion image and try to get a spectrum of one area compared to another. And from that, you will get spectra that look different. And interpreting this combination of spectra and images to basically tell a story from the data obtained and turn that into useful information for customers is really what we're doing with TOF-SIMS. Because we could just send out this and go, oh, here's your data, good luck. But unless you can extract information from that by interpreting the data, trying to understand, okay, why are these things different? What are the relation to the various species present? That's really our job when people submit samples to us. Okay, let's move on and I'll talk about some of the sample applications we're going to use to describe the utility of TOF-SIMS. We'll look at a polymer spectrum, a disk drive spectrum, a wafer, some organic contamination on surfaces, and then we'll look into imaging mode, looking at a flat panel contaminant, paint cross section. We'll take a sidetrack into the pharmaceutical world, and then also look at some depth profiling. So I guess this is one-dimensional, two-dimensional, and three-dimensional information. Okay. So this is what a mass spectrum in positive ion mode from a PET, polyethylene terephthalate, will look like. And this is what the spectrum will look like in negative ion mode. That's one of the advantages of TOF-SIMS. It's very easy to switch from positive mode to negative mode to look at electropositive or electronegative species, which provide each other with, nicely complementary information. So this spectrum looks a little complicated, lots of peaks, CH peaks down here, a little bit more complex here, and as the masses of species get bigger, the number of atoms in those molecules can be significantly get higher and harder to understand. We've color coded in this case the based on mass 104 is the breakup of this part of the polymer. Mass 149 is the breakup of this part of the polymer. And the 148 and 193 are the blue lines here. In negative ion mode, you see related but slightly different species. The 121 is basically the 104, but with an extra OH on it. The 76 is the benzene ring here in the middle. So this is a task where we kind of know the structure of the polymer. If this was an unknown material, we would be trying to identify these peaks, and from the identification of the peaks and the difference in mass between them, we would be interpreting these from a mass spectrometric perspective to determine the structure of the material under study, or the mixture of materials that we were seeing. Because in the real world, we almost never see pure materials. We almost always see a combination of materials, because things are made from mixtures, and contaminants don't behave nicely, and they bring other things along with them. Okay, let's zoom in a little bit on a different peak, on a different sample. This is from a disk drive. In distant past, the disk drive industry was very important to EAG, but it's matured and moved on now. So those products are generally using known technology now, and they don't need us quite so much. So one of the things used in disk drives are lubricants, and the lubricants affect how the disk performs over a long period of time. And you obviously don't want to lose your data, so you have to use the right lubricant. In this case, we've zoomed into mass 135 to identify that, and we can measure the exact mass, and from that exact mass, we can determine the likely molecular formula, which in this case is C8H7O2. These masses are almost the same, and there aren't a lot of other chemically sensible combinations of atoms that would make up that mass. We can zoom in on a different area of the spectrum. This is mass 59 near cobalt. So this is the atomic ion of cobalt. And then we have a number of other low molecular species there. There's a silicone-related species, an oxygen-containing hydrocarbon, and a fluorinated hydrocarbon, probably from the lubricant. But what you can see is in this small mass range, 58.9 to 59.1, there are 1, 2, 3, 4, 5, 6, 7 plus different species there. If we go back to the PET, imagine the richness of the information that you have at each of those peaks. So that makes it, the amount of information containing a TOF-SIMS spectrum is really huge. That's a blessing and a little bit of a curse, in that there's a huge amount of information there, but it can take a bit of time to determine what is significant. Here's another example, zooming in on mass 56 on a silicon wafer. Clean silicon wafer looks like this. There's a peak at 55.95. This is due to silicon 2. There's an oxygen-containing hydrocarbon and just a plain hydrocarbon. So these are just environmental species absorbed from the environment that the wafer's been exposed to. There's a very little peak here at mass 55.93 due to iron, but on the contaminated wafer, which had issues, there's a significantly higher iron intensity. And this is one of the cases where TOF-SIMS can actually quantify the amount of iron. We can use standards or cross-correlate with other techniques such as SIMS or TXRF and determine the concentration of species like this. And that's an extra step that we would have to take, but it can prove useful, particularly for looking at areas that are too small for TXRF, or too small for SIMS even, perhaps. Okay, let's move on here. So talking a little bit more about organic contamination on surfaces. In this case, it's a wafer, but this is actually relevant to a lot of industries where people care about the cleanliness of a surface. So wafer manufacturing and processing is an obvious one, but optics are another one, and medical devices are also a case where you have to know about the cleanliness of your surface, understand the surface chemistry, and make sure you're not introducing unknown contaminants during the processing of your material, whichever industry you are in. So airborne molecular contamination, I kind of touched on that a little bit earlier, but those are organic materials which can outgas or transfer or flow onto a sample from the environment of the sample is in. So in this case, those could come from cleanroom materials, process chemicals, the AC system, also from gloves, garments, tools, etc. that are the sample is exposed to. We have a nice reference spec library of materials that we've collected over the years so that we can hopefully identify unknown materials that are found on wafer surfaces or other surfaces. Okay, so here's another mass spectrum. We've kind of color-coded the species that we've interpreted to be related to each other, 149, 133, 105, and then this blue series as well. And those are quite common materials or ions seen on wafer surfaces. We haven't shown the low mass range, which would stretch off down here, and silicon would be on that, but it would be off the scale on on the scale that we're using here. So let's look at the next page and see what the identity of these species might be. Okay, so the 219, 203, 163 series are likely due to this material, Ergonox 1010. That is a polymer antioxidant used in a lot of industrial plastics to extend the lifetime of the plastics and to reduce their vulnerability to UV light. A common fragment ion from this is at mass 219. This is called the butylated hydroxytoluene cation. It's a bit of a mouthful, but that's this fragment here, and it's very diagnostic for this material and other heavier polymer additives that have that component in it. The other series of peaks, the 149, 133, 105 series, are most likely due to dioctyl phthalate or diisoctyl phthalate. That's another polymer additive. So that's actually a plasticizer that's used to be added to polymers to improve their flexibility and durability. So because wafers are often stored in plastic boxes and exposed to other plastic storage material during their manufacturing process, it's almost unavoidable to get materials like these onto wafers. So one of the things we always suggest to people is that if you can give us a control sample or a known good sample, that's hugely important to determine the significance of some of these very common species that you might see on a wafer surface. Okay, let's talk about some common contaminants. These are contaminants seen across a huge wide range of industries, from aerospace to semiconductors to optics and lasers to medical devices. Again, any industry that has a high level of cleanliness associated with processing samples. Common things, silicones, polyethylene glycol, fatty acids, glycerides, phosphates, sulfates, phthalates. These are all materials which tend to have, they're either surfactants, they're either tend to migrate to surfaces, they have low surface tension, they're very mobile. So those tend to be the common things that we see with TOF-SIMS. They're often accompanied by elemental contaminants, which are either environmental or human or other potential sources, such as sodium, potassium, magnesium, calcium, and then fluorine, chlorine, sulfates, phosphates, etc. That those are, we can often track down the source of these, but they may have more than one source in real life. So just because we often assign sodium, potassium to human sources, for example, because they come from fingers. However, they could come from a very large number of other potential sources too. So having a good experimental design when we're looking for contaminants or sources of contaminants can be very helpful with TOF-SIMS. Okay, let's move on. Okay, this is a residue on a flat panel display. Nothing visible in an optical picture, but here's the mass spectrum obtained from that area, and this is the total ion image obtained from this area. So the total ion image has a very obvious feature here, and if we do selected ion imaging of a silicone peak at mass 73 and a general hydrocarbon peak at mass 27, we see that these are inverse to each other. So this contaminant on this flat panel display leading to low pixel brightness was due to this blob of silicone located here. And this is an interesting example because this silicone is very specific to that location. Often when we see silicones, they can be widely distributed over the surface and not show a whole lot of separation. Okay. Another imaging example, this is a paint cross-section from a car. So car paint is a very well established industry, so that your car has a nice color, but also so the paint is durable and there's some hardness on the surface as well, so that it doesn't get damaged too easily with chips of stones from the road or other damage while driving around. This is an total ion image, which gives us a hint that we can see some layer structure here. There's the substrate. This looks like maybe the entire paint structure, and this is part of the sample mounting. This isn't part of the sample. So when we take some selected mass images of those, we can see there are distinctive layers. Then the chlorine corresponds to the primer paint. The CNO, generally indicative of nitrogen and oxygen-containing hydrocarbons, is indicative of the clear coat and the base coat, and the aluminum signal is from the base coat, potentially from a pigment in that. Then we have a magnesium coming from the substrate, which is probably an additive to the metal. So this is, again, illustrating that we can use TOF-SIMS to look at features on a surface and dig quite deeply into the different layer structures. I'm not showing any of the mass spectra here, but if we had taken a mass spectrum from this area, we would get a spectrum indicative of the clear coat. And we could compare that with reference spectra then as well. Okay, we're going to take a quick sidetrack into the world of pharmaceuticals. Pharmaceutical formulations are obviously very important and a little bit in the news these days with people looking for vaccines and things, but pharmaceuticals are obviously used in the treatment of all kinds of disorders and diseases too. So it's not just the pharmaceutical active ingredient, the API, that's important, particularly when you're delivering something by swallowing it. You want the drug to either get into your bloodstream quickly, so you may add a disintegration agent that helps break it up, get it metabolized in your stomach, or you may actually be trying to deliver a low dose of drugs over a longer period of time. So you want to protect it so it dissolves more slowly in your stomach and delivers an extended release over a longer period. So in this case, we're going to look at a drug called lansoprazole, which is a over-the-counter heartburn medication. This is the structure and the formula of the material. So it's got a lot of nice ions, and the more different atoms in a structure, the easier it usually is to see with TOF-SIMS, and the more likely we are to get diagnostic peaks. So this is an optical image of about a 1 millimeter microsphere inside the tablet, and we're going to image this 250 by 250 micron area. So these are some of the ion images obtained. Total ion image, showing that we have nice illumination over the whole area, and then some elemental species, magnesium, silicon, titanium. This has likely come from a magnesium silicate coating on the pill. Titanium's probably a pigment. Some polyethylene glycol, often present as a lubricant, hydroxypropyl cellulose, present generally to bulk up the material and for some stability, sucrose, same reason, and then the lansoprazole, we see very specifically two peaks here from mass 370, which is this plus a hydrogen, and mass 205, which I think is a cleave in the molecule right here. So we can identify these quite nicely and show that the lansoprazole is in the internal part of the drug capsule, and there's a coating around the surface. You can get an indication of that from the morphology here in the optical image, but we've got conclusive proof of the composition from the ion images. Why this matters quite so much is obviously in design of the product, but it's also highly important to understand the structure of your drug from an intellectual property point of view. When drugs come off of their patents and people then make generic versions, that can lead to legal conflict. So TOF-SIMS, along with techniques such as SEM-EDS and Raman mapping, can be one of the very powerful tools to understand where things are located on a sample. Okay, let's move back to technology again. This is an example of where TOF-SIMS can be used to look at hazes on a surface. Haze is usually something that only shows up under direct optical inspection, maybe with a UV light or some other light scattering techniques. But hazes can be quite hard to identify. Often they're just there in very small amounts and are enough to change the reflectivity or the apparent surface roughness of a sample, but there's not enough there to really measure by some of our more traditional techniques. In this case, when we do ion imaging of about a 500 by 500 micron area, we can see species due to the quartz substrate. Very bright, but we also see heterogeneous distributions of sodium and some glycol peaks, I think probably from propylene or ethylene glycol. And in this case, the only way we'd be able to get these with other traditional techniques would be probably to do a solvent extract with either ultra pure water or with a solvent. And in that case, you may get nice information with GCMS if we can dissolve the glycol component and do GCMS on it, but that wouldn't detect the sodium. But if we did ultra pure water extraction, we could probably detect the sodium through ICP-MS, but that really wouldn't tell you anything about the glycol. So again, this is illustrating TOF-SIMS being complementary to other techniques available for materials characterization. This is a biosensor example. In this case, we have gold patterning this is a gold ion image, and we are putting a self-assembled monolayer of material on there. That in this case, this is a alkane thiol, and the alkane thiol in this case, if you put it on there in a controlled manner, it can self-assemble into nice aligned columns, effectively, of this molecule. If we look at this gold plus sulfur image, you could say, oh, it looks right, like we've got nice strong adhesion of the alkane thiol on there, and it's only on the gold areas. That's possible. However, gold, particularly industrial gold, often has a high concentration of sulfur associated with it. So that's not quite enough evidence to say we have the alkane thiol on there uniquely. However, if we analyze the alkane thiol itself and do an ion image of that, we can see that it also is located on the gold features on this biosensor. So this is an important task or an important process to be able to functionalize surfaces. You could then introduce specific molecules that bind to these to turn this into something that's sensitive to a biomolecule exposed to it, and then measure a current or sense its presence perhaps. Okay, another biomolecular example. This is the printing of antibody droplets onto a polystyrene substrate. The blue is polystyrene, the red are actually antibodies, and or it's from indicative of an amino acid that's in the antibody, and the green is sodium chloride. So this is the as-received surface, and when we look at that to start with, we don't really see any evidence of these nice antibody droplets that we were expecting, and that's often because biomolecular solutions have high concentrations of buffers or salts in them, and this sodium chloride has crystallized nicely, as you can see from the ion image on the surface, and from that, we actually then rinsed this, it got rid of the sodium chloride, and that's what exposed the nice antibody droplets that we expected to see there. Okay, let's move on to some depth profiling examples. In this case, we're looking at our old friend PET again. PET polymer with, here's a small portion of the mass spectrum, so we've got hydrocarbons and oxygen-containing species. If we sputter a soft material or polymer with an oxygen beam or a monatomic argon beam, we will damage that surface. So the green's representing the sputter crater here, and this is a spectrum where you get after sputtering. You can see it's changed substantially. The carbon has grown, and a lot of the more diagnostic peaks up here have decreased, and we've got a lot more CH peaks down here. So we have clearly changed the surface of this material when we sputtered it with an oxygen beam. Okay, we can kind of mitigate some of that damage with a giant cluster ion beam or an argon gas cluster beam. On some of our instruments, we have a means to put an argon cluster beam onto the surface, which is usually maybe 2,000 argon atoms with a single charge. And that can basically remove the damaged area represented in green here. And then when we analyze after removing that damage, you get a mass spectrum that looks much like this, which is very similar to the red spectrum obtained on the as-received surface. So that's basically using the argon cluster to remove some of the damage induced by the monatomic beam. We can also show that in a profile. This is depth in this direction, signal intensity in this axis on a log scale. So you can see some of the diagnostic peaks, C7H5O, C6H5, they grow rapidly in intensity as we sputter through the damaged region. And the damaged region looks to be about just over 1,000 angstroms thick before we get up to a more steady state and through the damaged region induced by the monatomic ion beam. So this is kind of illustrating something that's not very easy to accomplish with beams such as cesium, oxygen, or just straight argon, because they induce damage in soft materials, whereas the cluster beam does not. And there's another example of that right now. Again, back to a reference film that was manufactured by a group in the UK at the National Physics Laboratory. They made a layer structure of these two different polymers. They're both called ergonoxes and they have similar functions, but they're very different chemical structures, as you can see from here. So they made this layer structure on a silicon wafer, 100, 100, 50, 50 layers of the ergonox 1010 interspersed with thin layers of the ergonox 3114. And we can get very nice molecular ions of those species using the cluster beam to depth profile. So in this case, we use the cluster beam to erode material, and we use our bismuth beam to acquire signal in between sputter steps. So what we can see here are 1, 2, 3, 4 spikes corresponding to the ergonox 3114, and we see a 50, 50, 100, 100, and 100 layer structure from the ergonox 1010 in between that. So that's a very nice illustration of us preserving information after sputtering with the cluster beam. And again, yeah, we'd like to acknowledge the National Physics Lab in the UK for those samples. Okay, another example of using the cluster beam to either clean a surface or to understand what may be going on with a polymer surface. Here we've got a Ziploc bag where normally you'd expect that to be nice and clean. But what we see when we image that is a distribution of this species called urusamide, which is a long chain amide. And what that is an anti-slip agent to stop the two surfaces of a plastic bag sticking to each other. So it's basically a lubricant. Usually they're in small amounts. In this sample, it seems to be segregated to the surface and quite patchy in nature. But it has a very diagnostic peak up here at I think 338. When we expose that sample to the cluster ion beam, we can see that the intensity of that urusamide peak at 338 drops down quite rapidly with sputter time. Again, this is on a log scale, so 10, 100, 1,000 times more intense than the baseline down here. So in parallel with that, a more diagnostic peak from the PE, from the, I think it's polypropylene in this case, stays very stable during the sputter process. So you can also look at ion images as you profile through these things. So here we have as received after 3 seconds sputtering, after 6 seconds sputtering, after 12 seconds sputtering. So you can see we're successfully removing the material, but not really destroying it because we still get some diagnostic information. Okay, that's the end of the examples, and I'd like to hope that we've given you a flavor for the type of information that TOF-SIMS can obtain during an analysis that can incorporate a mixture of mass spectrometry, ion imaging or mapping, and also depth profiling into the material. We don't always need all three of these, but for complex examples, it may be a case where we would take a large data set like that. So here's a summary for you of the strengths of TOF-SIMS. It can provide elemental molecular information on from thin organic films and surfaces. It is a survey analysis, so you see what you see. You don't have to choose what species to examine. It has part per million or lower detection limits. Small spot size, we can focus the beam to submicron, so we can look at submicron features. A little bit hard to get good mass spectra from submicron features, but you can focus the beam quite well. It has unique profiling abilities in that we preserve molecular information, can analyze insulators and conductors. That's different from things like Auger, or where Auger is a multi-electron process, so it's very tough to do on insulating samples. We're applicable, I hope, to a wide range of industries and sample types. I see it as a bridge between surface analysis with techniques such as XPS, Auger, and SIMS, and chromatographic methods such as GCMS and LCMS. The information that TOF-SIMS obtains is somewhere in the middle of those, so it can be complementary to both types of materials analysis. Limitations. Organic information can actually be quite hard to interpret, particularly without control samples or reference materials or a good database. So we think our experience over the last 20 to 25 years of doing TOF-SIMS has given us a solid background of experience we can share with our customers when it comes to interpreting the data. Samples do generally have to be vacuum compatible. We can analyze wet samples as long as we freeze them properly during the pump down process, but that's challenging. But we can if we have to. At times it's too surface sensitive. If the samples have been badly handled or exposed to other analytical techniques before we get to them, that means that we may see a lot about the history of the sample through handling rather than through this processing it was exposed to. Okay, so here's a little bit of a table summarizing its relationship of TOF-SIMS to some of the other adjacent techniques that I've mentioned a few times. So SIMS, not great at organic stuff, doesn't really get solid inorganic information. It gets elemental information that can be related to the inorganic stuff. TOF-SIMS, relatively strong across the board. Quantitation's limited. I didn't touch on that a whole lot in this talk, but with standards, we can measure some concentrations. XPS is pretty good there. It's limited in the specificity of the organic information it can obtain. And then I'm not going to spend a whole lot of time on these other ones, but they all are complementary in some way to TOF-SIMS, and you can often get data that is supported by two techniques rather than one, or supported by some imaging information at a higher resolution from something like SEMEDS compared to TOF-SIMS. Okay, just to get back to our smart chart here, we've just talked about TOF-SIMS, which occupies the central portion of the chart. And I would like to sort of just to emphasize the overlapping techniques that I consider good relationship or good cousins to TOF-SIMS: Auger, Raman, XPS, FTIR, and also GC and LCMS out here. Some of these have already been covered in our webinars, and some of them are still to come. So you should stay tuned for more seminars that will be coming up. Actually, one tomorrow and the upcoming weeks. A little bit about EAG again. I think you've probably seen some of these points if you've tuned into some of the earlier seminars, but client confidentiality is very important to us. We've been in business for a long time and understand that intellectual property is hugely important to our customers. And these are a lot more of our plus points that I hope you can read at your own leisure. And also we have ISO quality accreditations for many of our techniques in most of our locations. And for the techniques and locations that are not recovered, we're constantly working towards those. And we believe that's a strong measure of our confidence that we can get certifications for most of our measurements. Okay, and we believe we can help you solve your materials and engineering related product problems, and we would be happy to talk to you about any questions you may have.